Good afternoon, everyone. I extend a warm welcome to all of you to CERCA's monthly expert talk series once again, where we present national and international experts who speak on important issues related to climate change and air pollution. Well, preserving the climate on planet Earth is our joint responsibility. However, there has been an overexploitation of our planet without any doubt in very unplanned ways in the name of development, which has triggered a climate crisis. The major culprits, of course, are the GHG emissions caused by ever increasing carbon loads, along with some other incriminating heat trapping gases. But there is hardly any doubt that if proactive and preventive measures are not taken now, it may become too late to stop this irreversible change. There is an urgent need to fine tune the future developmental goals vis a vis minimizing the carbon emissions through the adoption of low cost, newer and greener technologies, and also expanding the scope of the corrective measures both vertically and horizontally to prevent this irreversible change. But do we really understand how climate change took place in the past and how they impacted the societies and how future climate projections are carried out? Today, we are delighted to have with us Dr. Yama Dixit, Assistant Professor at the Center for Atmospheric Sciences at IIT Delhi, who will be speaking on Paleoclimate reconstructions from Northwest India, a peek into past climate change and its impact on societies. Future climate projections are mostly presented as a percentage change from the current climate, which in turn is defined by the relatively short, about 100 years instrumental records that do not capture the full range of climate variability. Paleoclimate reconstructions offer a unique opportunity to extend the records back in time and to put the instrumental records in the context, thereby providing a robust baseline statistic that describes the climate system. This talk will focus on the reconstruction of the long term changes in the Indian summer monsoon during the current warm period, the Holocene, and using paleoclimate data from Northwest India, abrupt monsoon changes and their impact on ancient societies will also be discussed. Before I officially invite Dr. Yama to deliver her talk, I would like to introduce her to the audience. Dr. Yama holds a PhD degree from the University of Cambridge and possesses a postdoctoral research experience at IFREMER France and the Earth Observatory of Singapore. Her broad area of research focuses on proxy reconstructions and paleoclimate dynamics, changes in hydrology, abrupt climate change, and impacts on ancient societies. She also serves as associate editor for the journal Nature Communications Earth and the Environment and the Holocene. This talk would be of around 30 to 35 minutes, followed by a question and answer session of about 10 to 15 minutes. I now hand over the session to Dr. Yama and invite her to deliver her talk. Over to you, Dr. Yama.
Thank you, Mr. Hemant, for a very nice and detailed introduction. And good evening, everyone. And thank you very much, first of all, CERCA, for inviting me to give an expert talk as part of CERCA Expert Talk series. Today, like you've already introduced, I'm going to talk about how climate has changed in the past, how to reconstruct it, and how to sort of use it in the context of present climate, and also understand how future climate predictions can be better, can be done in a more sort of with high levels of confidence using such paleoclimate reconstruction. So I'll start with giving you the present context of what are the temperature changes that is happening now. So this image actually is a powerful image that comes from the recent synthesis report of the Intergovernmental Panel of Climate Change, IPCC, came out earlier this year. And what I would like you to focus is Yeah, here. So for example, for somebody like my parents who were born in 50s, they would have seen temperatures. So the colors here, first of all, denote temperatures. The yellowish shades is about global temperature change above the 1850 and 1900 level. So it's about 0.5 degrees of temperature change, average global temperature change, and above the 1850 and 1900 level. So somebody born in 1950, like my parents, would have sort of experienced a range of temperatures. So in terms of the colors, you can see it has gone from yellow to sort of orangish colors. So my parents were about 70 years old, have experienced about a degree of temperature changes that has also occurred globally. And for people like me who were born in the 80s, they have experienced also. So their starting temperature was relatively higher, but then the rate of temperature increase and the temperatures that we have experienced again is about 1 degrees or even 1.5 degrees. So there was about over 1 degree, so 1.1 degree warmer as compared to 1850 and 1900. And for children, for example, my daughter who's born in 2021 and somebody born around 2020 would experience a very different range of temperatures, starting from already 1.5 increase in 1.5 degrees from the 1850 or the pre-industrial level temperatures, and what sort of temperature these children, the current and future generation would see or observe. It all depends on the kind of emissions that we are going to make. So, for example, if we are looking at the mitigation and also a lot of carbon sequestration strategies, we can actually lower that range and we can sort of minimize that temperature change, which is again now a wishful thinking, but we can limit that temperature change to up to 1.5. But then if we go as business as usual, and if you're aware of the SSPs and the various emission pathways, they could be like business as usual emissions, and these children would experience really high, up to, I don't even want to say, but 4 degrees of temperature change by 2100 if we go as we are going as of now. Now, these are the sort of temperature, to put in context, temperature changes that have occurred globally, and globally. Now, if I look at the global temperature changes in terms of this figure on the left, again, these are all temperature changes that have occurred with respect to 1950 and 1980. On the bottom moving graph, there is actually the temperature changes in anomaly with respect to the period 1950 and 1980. And you see that these are, before 1950, they're all below the mean line, as you would expect. But as it's moving around 1950, it starts to sort of come at average, because that's where the anomaly is calculated at. But if you focus on the changes in temperatures in terms of colors on the globe, you see now the bluer shades are now changing into more and more yellowish and grayish, yellowish and reddish shades. So clearly, temperature after 1950 and to 1980 has actually changed, and it has been increasing since then. So 2013, 2014, more and more red shades, very less of blue shades. So the blue shade near Greenland that you see, it's because of the melting ice, so cold water coming in. So it's not cooling that is happening, regional cooling that is happening in that region. So overall, it's the global average temperature which are increasing, and the dark red shades are sort of dominating. Now, what I would also, we all know that CO2 is one of the main culprit that has been emitted, and major cause of such temperature changes is carbon dioxide levels in the atmosphere. Now, what you're going to see here is actually very different timescales. On x-axis, you have timescales. Now, it's a negative because it's going in the past. So it's 10 to the power 5, and it goes up to, so it's about 800,000 years. And what you have on y-axis is carbon dioxide in ppm levels. So if those of you who are aware, current carbon dioxide levels in the atmosphere is about 416 ppm. And here, what you're seeing is very less. So we're not talking about current carbon dioxide level anywhere here. So if we see the carbon dioxide changes, you see there's sort of a cyclicity or a pattern that has happened over the past. And as we kind of approach modern times, and after the advent of measurement and observatories that were set up, carbon dioxide has been measured in seasonally, and these records, you can see that it's been increasing. And now, if I put in context the current warming, and we go far back in time, like it's going back 300,000, 400,000, 500, nowhere near the recent past have we seen anywhere temperatures like this. So this is up to 800 years. So current CO2 concentration and global temperature extremes are really unprecedented. We have not seen such carbon dioxide levels in the Earth, even when the climate was actually changing naturally. There were many cycles in CO2, and Earth did undergo ice ages and non-ice ages period. It has not been observed. Now, it is not also been recorded in the instrumental records, because instrumental records are relatively very short, about 100, 150 years. So we do not know what would the Earth's natural response would be to such unprecedented CO2 levels. So yeah, so I would like you to focus on the figure on your right. On x-axis, we have the periods, current time periods. We are here somewhere. And these are the future emission pathways. So there's a sustainability road where we'll literally like cut down all the emissions. We'll resort to more renewable energy sources, and also try and mitigate and draw down CO2 from the atmosphere and sequester it in the oceans or geological or any other ways. Now there's also a middle road which kind of strikes a balance between what is emitted and also more and more that is sequestered, taken back on the Earth. And the other is again business as usual, which will go on its own path, and the emissions would be really, really high by 2250 and even higher by 2100, which are the future prediction models. That's what they say. Now, if we look at the carbon dioxide in ppm, so the scale here is actually somehow hidden, but it'll come back on my next click. And you can see that 2000 ppm is something that, if we go on the way we are going, we can reach up to 2000 ppm. And you wouldn't want to imagine what are the implications and ramifications of this in terms of climate is. Now, what has happened is in the past, now I'll take you in the past. So from 1950, if you go back in millions of years, Earth has actually seen CO2 levels which were really warmer than present. So if we are here now, somewhere here now, we have seen the Earth has seen temperatures which were like or CO2 levels which were like present, and even warmer, something that I was saying. So they are sort of analogs to future climate change, and the natural climate variability, if it has been recorded somewhere on the Earth, it's of use to us, because we would not want to know the natural response of Earth to future climate changes. Now, So to put in context, last year in 2022, September 19th, we had carbon dioxide levels of about 416.19 ppm. And I just checked like a couple of days back, it was 0.86. So it has increased by 2 ppm, and which is about 0.64%. So it's continuously increasing, and that's like annual change that has occurred. So, but like, how do we know that CO2 levels were such? How did we measure these? Because the instrumental records don't go far back in time. So I'll take an example. to show how we know that what we know about past climate. So here you have a climate record that spans about last 2,000 years. So on the x-axis, you have age in years. And on y-axis, you have temperature in degrees centigrade. So we all know that from 1850, when we started measuring temperatures, the observed temperatures have actually sort of shot up like this. And this is the instrumental record, and that is the total range of it. But reconstructed record from proxy data and archives actually take you back. But what is important to note is the range of errors that are associated with the reconstructed reconstructed data. So first of all, this is also the warmest multi-century period. So the temperature range has been from 0.2 to up to 1 degree centigrade. So this was the warmest multi-century period in more than 100,000 years. And again, this warming is unprecedented, and it was not seen in any duration during the last 2,000 years. Now, how do we know what proxy is and what to use and how to reconstruct? So I'll deal briefly about proxy systematics and what they are. So there are things called natural archives, and what these are natural formations and recorders of natural climate experiments. What they do is they preserve climate information, which could be in terms of precipitation, it could be temperature, it could be pH in the oceans, it could be actual CO2 level, CO2 in the atmosphere. And these are somehow preserved in various natural formations. So for example, the archives like ice cores, in Antarctica, for example, scientists are working on drilling ice cores, and the air bubbles that are trapped within the ice cores million years before can actually let you measure the exact amount of CO2. And that's where the previous CO2 long-term measurement or long-term variation was coming from. So these were actually actual measurements made on air trapped in the CO2 in ice core. So that is one. Then there could be tree rings. So tree rings actually a very good recorder of very small scale changes. So for example, if there is high rainfall, the tree ring width, there are tree rings which kind of grow depending on how much precipitation was there in that season. So if there's precipitation was high, the width of the ring would be big. So on and so forth. So tree rings can also kind of record information of past climate. There could also be corals. Corals secrete the reefs or carbonate material, which is basically corals, along with the symbiotic relationship with algae, of course, secrete these materials, and the carbonate composition is actually a true recorder of the past precipitation changes. And I'll mostly be dealing about carbonates, and I'll tell you in next few slides how it works. But this is to give you a broad view of how various proxies have been employed depending on where you are on the global surface. You'll have to look for the right proxy, right archive, and then kind of filter out which proxy to use. Now, proxies is more like it is in place of a variable. So proxies for precipitation, proxies for temperature, and archives are are sort of the library where all these proxies are recorded. So again, there could be middens. There could also be sediment cores that can be taken from lakes, from oceans, and they could also be speleothems. So speleothems are cave deposits. So in caves which are mostly made up of calcium carbonate, they have deposits like these, which kind of have annual bandings of exactly what was the isotopic composition of carbonate, and they record exact isotopic composition of rainfall, and you can reconstruct rainfall and precipitation changes from the various archives. What I'll be talking about today is, since this is mostly focused in Northwest India, and I'll be focusing on lakes in Northwest India, I'll talk about sediment archive. And so just to quickly give, using a cartoon, how this sediment archive work, let's say this is a lake basin, where the volume of water that is coming in with time is basically dependent on what is being put in. Let's say if it's a closed basin, there's no river or external flow that is flowing in. There's input of precipitation that is and then there could also be input from the runoff from watershed that gets rainfall from the same sort of monsoon clouds, and then there could be some seepage in groundwater that we can subtract, and the output or from this basin, the only way water is going out is through evaporation. So we can do very basic conceptual modeling or basic modeling where we can understand how water has changed, how the basin lake level has changed in this basin. But what I am going to talk about today is more on the side of carbonate shells. So I mean, my drawing is not that great, but then you can imagine that these are carbonate shells which live rather very small crustacean, or they could be protist in the case of oceans, and they literally float in the water column. Some of them, bigger gastropods, also live on the shorelines, and when they die, they get deposited at the bottom of the basin, and they keep accumulating like this. And basically when they make their calcium carbonate shell, they are basically taking up whatever that is there in the water in which they are living in. So all the water chemistry which has changed over time is being recorded in these shells, and as they die, they would accumulate one on top of each other, and basically recording the treasure of climate information through time in the sediments. So what we would do, we would go and, I mean, this is one of the gastropods that can be used, one of the example shells that can be used from the sediment sample. So what we do is usually we drill a sediment core in the lake basin if it has water, and if it is a completely dried lake, we call it a paleo lake. And I would show one of the pictures of such lakes, paleo lakes. You can drill a sediment core, or also just get a wall section dug here, and you can sample the section vertically. And as you go down, you're going back in time, and you're sampling. You're basically reconstructing. You're trying to reconstruct the climate record. So you take the samples back in the lab. This sediment core is then sort of sliced open vertically, and again, like, you can see various bandings which kind of denotes water chemistry, and that has been sort of preserved across several 100,000 and millions of years. Now, this is an example that I was talking about, that if it is dried lake, you can just kind of get a JCB, get the wall dug, and sample it at very high resolution to capture every snapshot of climate that has been recorded in lake sediment. So this is me during my PhD sampling in Northwest India. Now, what do we do with the samples then? We take it in the lab. We use various techniques. We pick these carbonate shells. Invariably, all water bodies, be it marine or terrestrial aquatic systems, would have shells, various shells, or various organisms which secrete shells or live in shells. We use these shells, the carbonate of these shells, and use a mass spectrometer to measure how oxygen and carbon isotopes in these calcium carbonate has varied through time, and then come up with a climate record. So basically, the isotope signal that gets recorded in shell carbonate is measured through time in the entire sediment core. Now, quickly on the isotope systematics. So calcium carbonate has one carbon atom and 3 atoms of oxygen, and in blue. So both carbon and oxygen can be used. So oxygen in particular is a really invaluable proxy, because it can be used in corals, it can be used in speleothems, lake, marine. So various archives can actually employ this proxy to reconstruct a past climate. And since I'll be talking about oxygen isotopes only, so I'll just deal a little bit into it. So oxygen here is actually coming from water in which these shells were living in. And oxygen has 3 isotopes, 18, 16, and 17. O18 is heavier isotope as compared to O16. So in turn, this water molecule would be relatively heavier as compared to this water molecule with an O16. Now, what happens is, during processes like evaporation, you would expect the lighter molecule, which would have a higher velocity, to escape the system first as compared to the heavier isotope. So in this mixture of lighter and heavier isotope water in this lake, for example, you would have the relative ratio of lighter and heavier isotope would change depending on how much of the lighter isotope has already escaped in the atmosphere. Now, there are various factors that also control relative humidity, temperature, and all, but then the ratio that this ratio is actually gets recorded in these shells, and then if you measure this ratio of O18 versus O16 in the in these shells in the lake sediments, you can actually reconstruct a whole lot of things, and which I'll talk about in a bit. So, these because of this mass fractionation process that happen during these physical processes like precipitations, for example, if it's rainy, you would expect heavier isotope to fall out or diffuse first as compared to lighter isotopes. So, if I say that a air parcel which has already dropped most of its moisture in Calcutta, and if it travels all the way to New Delhi, it would be relatively depleted in heavier isotopes because most of the heavier isotopes would have dropped on the way or before actually reaching Delhi. So the water that I'm drinking here or the rainfall that is falling here has a very different isotopes as compared to something falling close to Bay of Bengal. So, and that is the property that we use when we reconstruct precipitation using oxygen isotopes. So as a rule of thumb, so these are denoted, these changes that I'm showing, that heavy and lighter, these are really in third decimal places, which is why we measure them in per mil, so as parts per thousand. So they are denoted as delta 18O, and as a rule of thumb, we can just see that because I'll be showing some oxygen isotopes record. So if you see really positive values or high values, it indicates a dry climate. And if you see really low values or negative values, it is a wetter or more higher intense rainfall. So Northwest India, why Northwest India? One of the important factor is that it shows a very different sort of precipitation zone, going from subhumid in Delhi to semi or arid in Haryana and all the way to Thar Desert. So it is in a very short span of 150 kilometers. You can go from these to all these climate zones. And this region also has Thar Desert, which has the most sort of changing margins, and this is known as to be vulnerable to future warming and because of desertification, and it's been reported as one of the vulnerable regions. Now, another interesting point is that this region in the past was inhabited by Indus Valley civilization. So all the yellow dots that you see around Thar Desert here are Indus Valley sites. So they were actually living around these sites, and this is one of the largest populated Bronze Age civilization, contemporaneous with Mesopotamia in the Middle East and Egyptian society, Egyptian civilization in Northern Africa. So all these civilizations are developed around same time, around 5,000 years back, and the fate of these civilization is sort of still debated. What happened to them? Why did they leave where they were living? And that's where paleoclimate records also come handy to understand that. So I'll show you a paleoclimate record, and this is one of the very simple paleoclimate record reconstructed. That is what it looks like. So this comes from Haryana, one of the lakes, Kotla Dahar, that I just showed that I was sampling. I'll take you through this very quickly. So y-axis is the age axis. So if this is the top of the ground, I'm standing here, and as I dig deeper, I'm going back in time. So this is about 3 meters of sediment section, and it goes up to 7,000 kilo years. So 7,000 years. So 7 kilo years. And the proxies that I've used is how much of the carbonate material is there in the total sediment that has been collected at every interval. And I've also measured oxygen isotopes in blue. And these are ostracot shells. So these are very peculiar crustacean shell, which sort of change depending on, so their species changes depending on how saline or how salty the water is. So it would tell you what would be the conditions of living condition of water, or what the precipitation like at that would be like at that point of time. So if we start from like 7,000 years, so if we start from the past 7,000 to 6,000, it's really sort of a deep water phase with these shells indicating that they were in a very fresh water phase. Oxygen isotope, if you remember, if it's negative, it's wet. If it's more heavier or positive, it's dry. So it's relatively sort of negative, and it indicates that it is what was the deep water phase. There was also a lot of carbonate material, about 70 to 80% of carbonate material in this part. Now, as we move forward, it changed. The oxygen isotopes sort of increased a bit. The values are enriched as compared to this phase, and the carbonate also slightly decreased. So we think it's a shoaling or a shallowing phase. So there was less evaporation, less precipitation, and more evaporation that was occurring in this region. And this shell likes to live in saline waters. So clearly, shoaling phase or shallowing phase. After this, these shells disappear, and because they like to live in permanent water bodies, the lake became ephemeral. There was an stark or an abrupt isotopic change, but the lake became ephemeral after that, and the isotopes are more positive, and which means very dry and very less carbonate, so very less productivity in this lake. So if I were to talk in terms of the lake, so there was a shallowing of lake, abrupt drying around 4,000 years, and it was a 200 years drying, and then the lake became ephemeral. And we went back there in April 2023, and would you believe this is the lake? And it's not a very small lake. It's spread across hundreds of square kilometers, and we were standing on the lake. So if we dig about a meter or two, we would encounter water. So there's still lake inside, but the lake has completely dried up, and it's become ephemeral now. So ephemeral meaning seasonal. So when it rains during the monsoon season, this part gets sort of filled up, and then it dries out in dry season like April. Now, what is interesting is this 4.2 drying event, which was 200 years drying or monsoon weakening, which we have recorded somewhere in Haryana here, is also recorded at other sites. So, for example, this star is just off Indus River and in the Arabian Sea. So there's this peak in oxygen isotopes that has been recorded, and this star very close to the Mesopotamia. We see a peak here. Now this is a dust peak. Dolomite is a major mineral that is found in the dust in this region. So this is a dust peak in the sediment from this region, and there's also dust peaks in the Nile River discharge. So sediment record these dust peaks. So that means more aridification across these regions, which the archaeologists think could have led to the collapse or the deurbanization of these Bronze Age civilizations. So this is more of a global event. It was not a regional event that was recorded in Northwest India and that impacted the Indus civilization. So that also lays more sort of confidence that these are all very well constrained records that help understand how climate has changed, how it has helped the evolution of various societies across the world. Now, I'd like to talk about another lake quickly. I'm running behind time, but I would still show you this very interesting lake. Now, this comes from the Thar Desert. It's here. And would you believe me, if I were standing just behind this dune, you would not think that there is this big pit, or a big trench sort of a thing here. So this to give you a perspective, this is a 6 feet man standing, and this is a 6 feet sediment section that is there. And what these white things are actually quarried gypsum blocks. So gypsum is calcium sulfate, and this mineral is used for making cement and excuse me, plaster of Paris. And what you have here is just sand dunes. So, and gypsum is a salt which is precipitated out of water. So to make gypsum, you need water. So that means this was a big, huge lake, which was of course salty, but then gypsum was precipitating out. And it has precipitated because this is a 6 feet thick section and 6 feet deep sort of a lake, sediment accumulation. So clearly there was water for quite some time here. So So this is when we cleared it, and you can see these white massive blocks. These are massive 99 XRD results indicate 99% pure gypsum material with intervals of sandy events. So sandy events is when the clastic material or the sand and silt around it was brought in by the runoff, and then that's when the evaporation was not that high, that the salt gypsum was precipitating out. So this, we think, is relatively better in a climate with lesser evaporation as compared to units or intervals like these, where we had very high evaporation rates and the lake was precipitating out massive gypsum. So I've talked about gypsum, a little bit on the chemistry. Gypsum is calcium sulfate. It has 2 hydration water molecules attached. You can extract this hydration water molecule and measure a host range of isotopes like oxygen isotopes, O18, del 18O, del 17O, del D is the hydrogen isotopes, and also calculate various parameters like DXS and O17XS. So by weight, this water is about 20.9% of the total molecular weight of gypsum. So this is a very complex record, but I'd like to highlight a few things. So first of all, the bands that you see, which have been highlighted, are all gypsum bands, and these are dry periods. And to put in terms of timing, we go up to 11,000 years. So between 11,000 and present, there were intervals of very dry periods in between. But since we are focusing on just the early Holocene, or in context of these civilizations, let's just focus on this unit. And also, in the interest of time, I'll just quickly move to this unit. And this is the sandy unit that I was telling, that evaporation was not that high, and there's not much gypsum. If we look at the oxygen isotopes here, oxygen isotopes are relatively lower as compared to afterwards when we measure in gypsum here. So clearly, this was the wetter periods, and even wetter in the darker blue shade here. And archaeologically, this was the period of early development of early Harappan sites around this region. So this red dot here is the lake, and these are the sites that were developing around this region. And this was the urban phase, which started in 4.5. So this very light oxygen, or very depleted value of oxygen isotopes, or very wetter phase, is actually coincident with the development of urban phase here. Now, what happened afterwards is the drying that happens around 3.9 kiloyears. And interestingly, archaeologists at Cambridge, what they discovered is that most of the Indus archaeological sites, which belong to this period, post-urban period, they are concentrated eastward. So this drying that occurred in this lake, they are sort of following that, and they're moving towards the Indo-Gangetic plain. So we think that the drying that occurred, and this may have been a water source to these societies. So clearly it could have played a role in sort of in this whole deurbanization or movement, eastward migration of the sites. Now, so looks like past climate do tell us something, but how do they inform the future? So this is IPCC AR6 report. And what you see on your screen is a map of the world, and the hexagons are they've segregated hexagon as various regions in hexagons. For example, CNA here is Central North America, East North America is ENA, and I'll come to the region of interest, which is South Asia. We have East Asia, ES, Tibet, TIB. So on and so forth. The colors here denote increase in precipitation, observed increase in precipitation. And what they are trying to see, whether or not this is a natural increase, or is it the human or high emission induced increase. The dots that you see here are actually the level of confidence that they have on this inference that it is human influenced or not. So most of the dots are one dot, particularly this part. They think that the precipitation has increased, but they don't know whether we don't know whether this is because of human influence or is it the natural variability. Now, one of the major reason for this is that there is a lack of data So one dot is very limited agreement. Most of the records point in different direction. Proxy records point in different direction. So the three issues, if I can sum up, that are still sort of, is the gap to using paleoclimate to sort of, help better future projection, is there's very limited long-term reliable climate data. So we need more climate reconstruction like the ones I showed you from South Asia, not just South Asia, but other regions also, to give a global picture. Second is the resolution of measurement that, for example, Indian Meteorological Department is doing. They're doing it every day. They're measuring every precipitation event. But proxy data is working on other completely different scales. So, for example, tree ring, yes, we can measure seasonal, but for example, the other ones that I was showing are thousands of years. So, can we actually get to that resolution? So, we need a lot of research into developing the proxy or methods to sort of join those dots and bring it together. The other thing is that there's real heterogeneity in the proxies. So one proxy sometimes indicate that there was a very intense rainfall, and the other points in the other direction. So the resolution is also sometimes a problem. So we cannot get an average value for the entire region. So we can use some of the statistical tools, and my PhD student Akanksha and Anubhav, they're working on sort of resolving this problem of joining the IMD data, the measure data from Indian Meteorological Department, and what we have from proxy data. And what they're trying to do is to put more reliability on the proxy data, and these archives are the ones which actually can be extended. So IMD has divided India. Now this is work in progress, so I'll just briefly touch upon this. What we are doing now is IMD has divided India into 4 different zones: Northwest India in red, Central India green, Peninsula India in orange, and pink is the Northeast India. And there is rainfall data, but proxy data is really little. So these yellow dots are the only proxy data that we have that are relatively high resolution to compare with the IMD rainfall data. Now the problem now comes that they are on different units. They are either tree rings width, so tree rings width, or oxygen isotopes, or like really different units. So we needed to find a statistical solution to it. So we came up with this Z score, which kind of, so all the proxies were converted to Z score, which is basically the degree of deviation, which is from the mean. So how much the raw score deviate from the mean times the standard deviation. So for example, if it's a positive raw score on a proxy data, that means that it is higher, the raw data or the proxy point or measurement point at that interval or at that day, the rainfall was higher than the mean. So using this, we have actually plotted in black the IMD, in black the proxy data, and in blue IMD data, and you can see very nice correlation. So so the reconstructed data from various archives, natural archives, fits in very nicely with the actual measured data, and this lays really more confidence, and the regression curve. So R square value is about 0.8. So really good correlation value, and what we think is that this really kind of boosts our confidence that these archives are the ones we should focus and really take it long term. The other thing is the droughts that we saw that are recorded in IMD data are also recorded in very negative Z score. So if you remember this plot, it means that the rainfall in these regions were very low when the IMD data was recording low rainfall. So yeah, this is work in progress, and I'll end my talk by thanking various institutes that I've been at, and also a lot of the funding agencies, most importantly, Bill and Melinda Gates for the Gates Cambridge Scholarship when I was at Cambridge, and other fellowships that I've been awarded, and a lot of people throughout this journey that were a part of this work. So yeah, I'll end my talk here, and thank you for your attention, and I'm happy to take any questions.
Thank you, Professor Yama, for a very insightful presentation and sharing your research experience and thoughts with us. So now moving to a question answer session. We have a couple of questions in the chat box, so I'll read it for you. There is a one question from Manmohan. Are grain sizes good proxy or not for studies paleoclimate?
Yes, grain size is it is one of the first order proxies. So before going into direct oxygen isotopes or more on the isotopic measurement. Grain size tells you about what sort of environment of deposition it was that was there. So if it's grain size of any deposition. So yes, it's a very good first order proxy. So you can start with grain size and then build upon using various other more chemical and physical methods.
So next question is from Ahan. What do you think caused the 4.2K year drying? Also, could you recommend some studies that offer a long view rainfall proxy data across the Indian subcontinent? I have been using studies that use Speleothem as a proxy, but am interested in other proxies as well, specifically high resolution data for last 5 to 10K years. Thank you.
Okay. So there are two parts. First part, I already had it in one of my backup slides, which I thought I would show. Now, the main reason for the weakening of Indian monsoon around 4,000 years was the increased frequency of El Nino events. So I'd quickly like you to focus on this plot here. These are stack of various paleoclimate records from all over the world. So the bottom one is the Kotla Dahar record that I showed. And then there is record from Northeast India in purple. There is record foraminifera record from Arabian Sea. And just for your reference, x-axis, they're all plotted on x-axis, which is the time scale. So 0 to 7,000 years. There is Gulf of Oman dust peak record, and then Kilimanjaro ice core records here. And this pink bar that runs across shows that, there is something happening around 4,000 years. Again, so like globally, it has been recorded. What is also interesting is that the El Nino events, now this is coming from Galapagos Island, where the El Nino, it is essentially an equatorial Pacific phenomena. That's where it happened. So El Nino essentially increased. So there is a coral hiatus starting at 4,000. It continued for a long time. So we think that this El Nino would have been instrumental. And this is the general consensus until now for this abrupt 4.2 kilo year drying, that El Nino could have played a role in this. As for the proxies for long-term, Speleothem offers really great insights because they have a very good resolution in terms of the dating. So the absolute uranium thorium dating can actually lead you to even few days of resolution, which is great if we are comparing it with IMD data. So Speleothem, so there are several Speleothem records, but then now there are also several lake records that are coming up, which we are trying. In fact, some Akanksha and Anubhav, so some of my PhD students are working on lake records from northern India, and they're trying to kind of work on really long-term Holocene records, but high-resolution proxies.
Okay, so our next question is from Rohan. The question says, is there any density stratification within lake system that can alter the proxies that you used in around Thar Desert, since density of water is temperature dependent?
That's actually a very good question, but it would matter more for the oceans, not so much for the Thar Desert, for the proxies that we are using, because these ostracods, they live on the surface. So they would always need to live on the surface, needless of what density of waters it has been. But then if you're talking about oceans and we're talking about the other foraminifera carbonates, the foraminifera now can be benthic, which like to live at the bottom relatively deeper. And then even planktic can live at various depths. So that's when density, planktic foraminifera, that's when density plays a role as to where exactly. So we are reconstructing ambient water conditions using the chemistry of carbonates, right? So we need to know where this foraminifera was actually, foram shell was actually living to reconstruct. So that would actually help to know what were the density changes. So yes, it would impact in places where, depending on what proxy and what archive you're looking at.
Okay. So in the interest of time, we have been taking the last question. So if the question is, any prediction or forecast normally depends on recent data records. How does Paleoclimate data fits in?
Yeah, I mean, it goes back to the same slide that, we're trying to bring it, really stretching it forward in terms of resolution, in terms of uncertainties. The models are, at the end of the day, best guesses. They're not actual data that has happened or that is going to happen. But to bring in more confidence to the models, we need measured or data that has actually happened. So past climates do have a lot to say, but we are still in that stage where more research need to go into proxy development, better chronology, better resolution. First of all, more data, more paleoclimate data. So this slide was actually just that. So yeah, don't have a direct answer to that.
Thank you, Professor Yama, for answering all the questions. So, moving to our formal vote of thanks part. So, I, on behalf of CERCA IIT Delhi, want to extend my sincere thanks to you for accepting our invitation to deliver this talk. And it was a real pleasure to host you as our expert speaker this month, and we appreciate you for sharing your insights and expertise, shedding light on the critical aspects of climate history. And we also thank all the participants for your attention, and thank you for being part of the conversation and make the talk interactive through Q&A session. We will announce our next scheduled talk via social media handles very soon. Stay tuned for more impactful events in the future. Thank you.
Thank you
Thank you.
very
Thank
much,
you.
Dr. Yama. Thank you very
Thank you.
much.
Thanks. Thanks for inviting.